So, we have reached the most interesting and intriguing part of our work, to crystallization. What you have at the beginning of crystallization determines will you get crystals or not. In other words, input determines output. The first and most important thing is the purity of the protein preparation, its concentration, as well as its uniformity and lack of aggregation. The purity of the sample is evaluated on electrophoresis. The next key to success is the correct choice of precipitants and the method of crystallization. What we will have at the exit, if all the requirements are met at the preparatory stages, it will be nucleation, the beginnings of crystals growth, and finally, perfect protein crystals and defined protein structure. For example, on this slide you can see crystals obtained in the Institute of Protein Research. Now I will try to figure out what methods of crystallization of macromolecules exist. What are they? Advantages and disadvantages. One of the most widespread crystallization methods is the vapor diffusion method in a hanging or sitting drop. For this method, glass or plastic tanks are usually used. The tanks can be isolated or joined in plates by 48 or 96 units. In this method, vapor diffusion occurs between the drop and the counter solution. The hanging drop is located on a siliconized glass, which is fixed to a tank, with a counter solution with the help of vacuum grease. A drop contains a mixture of a protein with a counter solution. The concentrations are higher in the reservoir, so over time the water evaporates from the drop and condenses in the counter solution, which leads to a balance in the salts, concentrations, and subsequent protein crystallization. There is the equal process in a sitting drop, but a sample is located in a small well rising above the counter solution in a common tank. The next type of crystallization procedure is microbatch, the method of crystallization under paraffin oil. The protein is mixed with a precipitant solution in proportion 1:1 or 1:2. Drops are coated with a layer of paraffin oil for evaporating slowing down. After some time in these drops, protein crystals will appear. The third method is microdialysis. The protein sample is placed in a dialysis cell, which is placed in a reservoir with a precipitant that can migrate through the membrane to the protein. Membrane has pores of exact size. The concentration of the precipitant thus tends to become equal in all reservoirs. Concentration of a protein becomes higher and protein crystals appear. And the fourth method is crystallization in capillaries. A drop of counter solution and a drop of protein preparation with air layers between them are sealed into a capillary. Or it can be variant when drop of a sample situated between two drops of counter solution. Using this method, we form a concentration gradient and a gradient of the size and number of grown crystals. You can see it on the slide. This method is also convenient for obtaining a large number of small crystals. Now, let's try to understand when and what happens in a drop during the crystallization process and what nuances exist. For this purpose, I am showing you the diagram of crystallization, what we can see on it. Crystallization diagram shows dependence of protein concentration from adjustable parameters. The solubility curve on this slide is defined as the equilibrium between the presence of protein in solution and in a crystal. The supersolubility curve separates the conditions under which nucleation occurs from the conditions under which the solution remains pure. There are regions where concentration of protein here is very low, so crystals do not grow in this zone. It is the unsaturated zone. If you put crystals here, they are going to melt. In precipitation zone, proteins precipitate because the concentration is too high. In nucleation zone, crystals can appear and grow. Metastable zone. Here crystals grow, but they cannot appear here. Now, let's try to illustrate the crystallization process in a drop on this diagram. The black dot is the initial condition in the drop. We're still in unsaturated conditions. During crystallization, due to changes in some properties of the system, the proteins in the solution go into a supersaturated state. This occurs due to the diffusion process by gradually increasing the concentrations of substances that reduce the solubility of the protein. So the drop evaporates, the concentration of protein and precipitators increases, and we reach the nucleation zone. The dotted line shows us how equilibrium is moving. The critical cores of crystals are formed. I should say that nucleation is a very important step in crystallization.
И как только начинают образовываться зачатки кристаллов, для зачатка кристаллов хватает там буквально 10-100 молекул. Как только они начинают образовываться, уже спонтанно начинают образовываться кристаллы и расти кристаллы.
As soon as the smallest stable critical core has formed, crystal growth will follow spontaneously. Nucleants can contain from 10 to 100 molecules. Okay, as nucleation begins, it removes the protein from the solution. The protein concentration in the solution decreases. It is shown by the black arrow on the diagram. Consequently, we are moving into a metastable zone, but in it, crystals can still grow from the crystal cores formed before. So we can see growth of big crystals. This is very useful and convenient diagram. You can use it to understand what is happening in a drop and what to do further. We will return to it a little bit later. So, nucleation and ways to influence it. I'll repeat. The nucleation is a moment when critical cores of crystals are forming. What to do and where to start. Although the crystallization process is actively studied and used, it remains a trial and error process. Nucleation and crystal growth depend on many factors, such as temperature, pH, precipitator, concentration of salt, and sample. Testing all possible combinations will take a very long time and will require a lot of protein. Therefore, there already exists commercial crystallization kits containing the most popular solutions, covering a wide range of conditions. It's easier to start researching crystallization conditions with such kits. Even using commercial kits, it may be necessary to check hundreds or even thousands of conditions. Therefore, experiments are carried out in 96 well plates for crystallization and often using a robot for crystallization.
Количество даже при условии этих коммерческих доступных наборов условий очень огромное, то кристаллизацию удобно начинать в микроколичествах с помощью робота.
Firstly, it saves time and your efforts, and secondly, the amount of sample. So I advise to start with robot crystallization. On this slide, you can see one of the existing crystallization robots and plate for it. You can see such plates for robot crystallization contain 2 or 3 wells per 1 counter solution. It makes your screening more productive. 3 different proportions per 1 condition, or 3 different samples per 1 condition.
Это ускоряет процесс. То есть вы в одной 96-луночной плашке можете сразу 3 разных условия для одного образца взять, точнее, 3 разных
At least 3 components per solution are used: protein, pH, or buffer solution, and participant. We can change buffer, precipitant, and concentration of components. What can we change else? We can modulate temperature. Temperature is another factor influencing crystallization. We can place crystallization plate to the room temperature, or on +4 Celsius degree, or into thermostat on any chosen temperature. I mentioned about it on one of the first slides in the lecture. So for screening crystallization conditions, I recommend always beginning with using robot facilities and commercial kits, covering a wide range of conditions, and test different temperatures. Only then you can proceed to systematic screening to optimize the conditions selected at the first stage.
Какой-то намек на нуклеацию, на начало зарождения кристаллов. И только потом переходим к систематическому скринингу, к оптимизации условий кристаллизации.
Thus, we smoothly moved on to optimizing the crystallization conditions. Let's talk about it. For example, what can you do if you have a lot of small crystals? You need to stop nucleation, and then there will be fewer larger crystals. Here on the slide, you can see the beginning, a lot of small crystals, and after improving small amount of big crystals. How can we do it? We can reduce the protein concentration. It can influence the amount of nucleations and subsequently the amount and size of crystals.
Понизить концентрацию белка, например, изначальную. Это может сказаться на количестве изначально выпадаемых ядер кристаллизации нуклеантов и, соответственно, уменьшить...
Also, we can reduce the ratio of precipitant volume to sample volume. The equilibrium will be achieved more slowly, and therefore, as a result, large crystals. What else? We can reduce evaporation, reduce nonspecific nucleation by blowing dust particles off the glass or centrifuging the sample before making the drop. It will also help us to reduce the amount of crystals, but enlarge their size. Besides that, we can change crystallization temperature or vary the pH, completely change or make a pH gradient between the drop and the counter solution. Slow moving of pH from drop to counter solution will improve the quality of your crystals.
Можно сдвинуть температурный режим кристаллизации. Можно поменять pH буфера. Можно сделать градиент pH, когда у вас в капле один pH, а в противорастворе другой. И плавный переход от одного к другому тоже будет улучшать качество получаемых вами кристаллов.
One more way is to use additives, such as glycerin, organic solvents, or divalent cationic detergents. Drop will become more viscous, hence fewer nucleation. By the way, very often additives can also serve as cryoprotectants necessary for the collection of X-ray structural data in the stream of liquid nitrogen. It is very convenient when the crystal was formed in conditions that can protect the crystal and prevent its destruction at sub-zero temperatures. Since the transfer of the crystal into cryoprotective solutions that are not native for it is always a stress for the crystal, it can collapse and stop diffract X-rays. There is another way to optimize crystallization. It is seeding. It helps to increase the probability of crystals' appearance or optimize conditions. If we recall the crystallization diagram, there is a metastable zone where crystals do not nucleate, but can grow. Therefore, if you add crystals from another drop to a drop that it is in a metastable state and unable to reach the state of crystal nucleation, then they appeared in conditions favorable for growth. It will begin to grow actively. In this way, we will be able to obtain individual large crystals. The number of transferred crystals and their size are selected experimentally. Sometimes you will need to do several dilutions to achieve single crystals. On this slide, you can see a drop with a big amount of small crystals. Drawing a stroke by drop with crystals, and after that by clear drops, we've got a titration by crystals. In the second drop, we've got less bigger crystals, and in the third drop, a few big, good crystals. A needle can be used for seeding, but the best way to transfer is the whiskers of cats or dogs, or the hair from a horsetail. They are quite elastic and flexible. In addition, crystals are better sorbed on them. If you have cats, dogs, horses, do not miss the opportunity to pick up their hair and put it into action.
Усы кошек или собак, ваших домашних питомцев, или волосы с хвоста или с гривы лошади, смотря кто у вас дома есть. И именно этим волоском перенести кристаллы.
The next is a crystal quality. So you've got crystals, beautiful, large, but isn't it a salt? There is a special paint to check it. It penetrates into the crystals of macromolecules and colors them. But it cannot penetrate into salt crystals because small salt molecules placed too tight to each other. Use glutaraldehyde. He would rather fix a protein crystal than dissolve it, and it gives it a yellowish color. The crystal of salt will melt. A rather barbaric way is to try to break the crystal with a needle. Protein crystals contain a lot of solvent, up to 40%, and salt crystals may not contain it at all. Therefore, protein crystals are more plastic, and salt crystals are as strong as stone. If you take a needle and poke it into a crystal and it crunches, then it's a salt. And if it melts and smears, then it is a protein crystal. Another way to distinguish protein from salt is to catch the crystal, wash it off from the solution, and set an electrophoresis. If you see the right band, it's protein crystal. No, it's salt. The most proven, but not most accessible method is to place the crystal on the X-ray beam and see if the crystal diffracts or not. Using this method, you will get unambiguous results. You are going to know protein or salt. And do they diffract, and can you use it for data collection or not? And finally, if so far it has not been possible to crystallize your native protein, what do? Then you need to go back to the very beginning and radically change genetic construct. Here I'll tell you the strategies for successful subsequent crystallization. So if protein has unstructured moving parts, which, of course, are not strictly necessary for its functioning or folding, then remove them. Leave only functional, not moving parts. It will be much easier to crystallize such protein. If there are several domains in your protein,
если все-таки вам не удалось получить кристаллы хорошего качества, что же делать? Мы будем возвращаться на этап в самое начало. Мы можем вернуться и поменять конструкцию, генетическую конструкцию для наработки вашего белка. Тут я вам расскажу стратегию для успешного.
And they are very flexible. Then get each domain in an isolated state or somehow fix them in one position. Make the interdomain binding unflexible or add a partner, cofactors, ligands, that will contact with domains and fix them. One more way is to mutate the individual residues. It will remove the mobility of some areas, will reduce the aggregation ability, and give thermal stability. It will help you to crystallize your protein and solve its structure.
И еще один способ – это провести мутагенез отдельных аминокислотных остатков, что тоже может помочь уменьшить какую-то подвижность каких-то доменов, каких-то петель, что приведет к большей вероятности того, что вы закристаллизуете ваш белок и определите в дальнейшем его структуру. На этом моя часть лекции.
On this point, my lecture is finished. I wish you success in this difficult task. Large, well-reflecting crystals to you. Hope that my lecture will help you in your scientific work.